The broadcast is now starting. All attendees are in listen-only mode.
Good morning, and thank you for joining us today for DC Power Systems. Today we're going to have Ryan Stankiewicz, head of our technical support department, discussing all the components as well as some common technical support failures that we see and a few very interesting cases as well that he's seen in his time in technical support. If you have any questions during this webinar, please feel free to put them in the questions box, and we will answer those as they go along if they're relevant to the conversation, or we will answer them at the end if there's something outside of that scope. Ryan?
Thank you, Sue. Good afternoon, morning, everybody, depending on where you're located. We're going to go ahead and get started here and go through DC charging systems. The goal of this is kind of a high-level overview from soup to nuts, starting at the solar array, working our way through to the system itself. Not design in any way, but some of the common issues, sizing and stuff like that. So as Sue mentioned, definitely raise your hand, ask questions as we go. Don't keep them for the end, because if you're like me, you'll forget what you were thinking. So again, like I said, what we're going to do, just a quick run through who we are. We want to talk about the PV array. Dealing with rapid shutdown on a DC coupled system. That's becoming a real thorn, I guess you'd say, in people's sides around here. Proper switches and OCP over current protection. Combiners, charge controllers, the balance system, where to put your surge arresters, and of course, a lot of my wall of shame pictures. So I'll ask a lot of times when somebody calls in for support, I'll ask for pictures of stuff. And I find it so much easier to understand what you're looking at if I can see it as well. And that helps a lot in the troubleshooting scenario. And if they're really entertaining, I end up using them in a slideshow.
One more brief thing I forgot to mention. If you do want NABCEP credit for this presentation, it is good for 1 hour of continuing education credit. Please email sales@midnightsolar.com after the webinar if you do need the certificate for that credit. Thanks.
Yes, good point, Sue. Thank you for that. Yeah, sales@midnightsolar.com. So Midnight Solar, most of you probably aware who we are. We, as a company, have been around for about, I think, 14 years now. We build everything from breaker panels to charge controllers to lightning protection to rapid shutdown. As a group of people, we've been around since trace engineering, so we've been doing battery-based systems for a good long time. Probably been there, done that, and seen it in some form. So, generally speaking, we can help you get out of about any bind that you're in when you're working on these systems. So some of the important things for a PV array to think about: the max VOC, the effects that temperature have on the max VOC, parallel strings, and the voltage of each string, the series modules, and the current of each module. We're going to talk a lot more about this, but these are just some of the things we're going to hit at, and the max wattage of the array. So voltage, this is one that some people trip up on sometimes. It's a common one we get a call on, especially in the winter and in the summer, believe it or not. There's two things to think about here. Over voltage and under voltage, and we'll talk about both. But first we want to point out that equipment will have model numbers, and those model numbers don't always equal what they really are. An example of that is when I worked at Magnum, we had a charge controller we called a 200 volt charge controller. And when you started reading the specs, it operated to 187 volts. At 188 volts, it went into resting and didn't operate. So if you just looked at that and said 200 volts, okay, I can do 190 volts open circuit, life is good. Don't always trust the nomenclature you're seeing. Always look for that MPPT window or that max operating voltage. That's another key that you'll see in there. That's true for a grid tie inverter as well. They all have different windows. They all have different max voltages. On our products, we try to stay with the nomenclature. So if you see a classic 150, it'll operate all the way up to 150 volts. If you see a classic 250, it operates up to 250 volts. So on and so forth. So that's just something to be aware of, that you don't over voltage the controller. We talk about whether we use the record cold or the average cold. And if you're using a classic, for example, it has a function called hypervoc, and that allows us to overvoltage it slightly and not damage it, but it will not operate. So what that does for people like me up here in Maine, where it gets really cold, is it allows me to design around the average cold. I can look at the weather records here and say, okay, it gets negative 15 degrees, negative 20 degrees fairly regularly. That's the number I'm going to use to design my system. That morning it gets negative 40. The controller is just going to stay in resting until the modules, warm up a little bit and the voltage drops, and there'll be no damage done. But that's not always true. Some equipment out there, it's a pretty hard number, and if you exceed that number, you will do damage, and it, generally speaking, is not covered under warranty. Most power electronics will monitor their overvoltage. So something to be very, very diligent about is your maximum voltage. Don't push it. Don't try to push it, way to the limit. And the other thing holds. Like I said earlier, we get those same calls in the summer. It starts getting really warm in July and August, and people are like, well, my classic is resting, and it's pure sun on the array. The minimum VOC. Most of your battery-based MPPT charge controllers require about 133% of the actual battery voltage in order to wake up and do something. So if you have designed that array really close on the voltage, and then we get a good warm day, that voltage is going to be too low. And I should justify that a little bit by saying that, if you look at your module, it's going to have a temperature coefficient. And basically, in a nutshell, what happens is as the module goes below 70 degrees Fahrenheit, its voltage it goes higher than what it's actually on the nameplate. So if your module says it's 44 volts even VOC, that's at standard test conditions. As we start getting colder, that number will go up, and it can be pretty significant. You can see another 20% on that voltage if it gets cold enough. And the same happens on the other side of that coin. As that module temperature goes above, say, that 70, 75 degree area, the voltage starts to drop by the same amount. So if you get a module that's 140 degrees, it could drop, 15% in voltage. So that's something to be very aware of and just, consider. And that example I was talking about the 133 volts, that's not above the nominal battery voltage, which is another common mistake I see. That's the actual highest voltage you're going to charge to. So let's say you have a set of Trojan flooded batteries and you're going to equalize to 62 volts. And don't hold me to that number. Look at your Trojan data sheet. But we're just using this as an example. 62 volts would be 83 volts minimum VOC from the PV array in order to wake up. So that's your bare minimum. We all know that you cannot adjust module voltages. So if you're using, say, 60 cell modules, you probably want at least 3 in series. If you're using 72 cell modules, then 2 is going to be right on the edge for a 48 volt system. 3 might be really good. You just have to run those numbers. Our string sizing tool will take that into account as well. It'll tell you if your voltage is going to be too low on a hot day, as well as too high on a cold day. And we did talk about HyperVoc, but it does bear a little bit more explanation. Like on the Classic I was talking about, you get the battery voltage added to the model. So if you've got a Classic 150 and you've got a 48 volt battery bank, it is safe to 198 volts. Now it will stop operating at 150. So if your VOC is 151 volts, it's not turning on. So remember, it is a non-operational safety zone. It is not it's not like a grid tie inverter where they say the VOC is 500 volts, but the MPPT window is 450 to 250, for example. You cannot design into that area. That is only for those record cold mornings. We get that 40 below night, and the modules get really powerful on voltage, and they're up here in that HyperVoc range. But as soon as the sun hits them, they wake up and they go right to work. So it's just that's all it does. It allows us to design around a average cold in areas like this. And it may be that case where, okay, now I can get 3 72 cell modules on a Classic 150, for example, and not have to worry about damaging it if it gets cold out, or 5 60 cell modules on a Classic 200, just depending on where you're at. Again, lean on that string sizing tool and definitely call us if you have any questions. So now we're going to go to some pictures. We're going to talk about stringing modules. This one here is an interesting one. The complaint that I took on this call was that they had an east and a west facing array, and they had 2 strings of 3, and the Classic wasn't tracking properly. Well, it turns out that one of the other modules over here, this is 4 and this is 2. So of course, when you add one module over here and the other 3, this one string is never going to track correctly. So, while I'm picking on that for this, the end of the story here is that if you just moved that one module back over to the right-hand side of your picture over here, and you had 3 east and 3 west, while it's not perfect, the losses are going to be fairly minimal, as that tracks across the day. Because the MPPT voltage is typically based on, the amount of sun on the module. It's not really, it's got to do more with shading than it does actually indirect sunlight. So, while it's not perfect, and I would generally recommend 2 MPPT controllers, what I typically tell people when they ask is, go ahead and try it. And if you find that you're losing a lot, put in a second controller. But if you're not, then maybe it's not worth the cost of the second controller for that extra 4 or 5%, whatever you may be losing. So one of my favorite things to do is design solar arrays using piles of modules that are not matching. Any of you that have been doing this for any period of time, especially off-grid, knows that back, 15 years ago, modules were expensive, and that was kind of the one thing that the customer could never really afford many of, and you'd always end up going back and adding a few modules every time they had a little extra money. And I like to call that solar salad. You were mixing a bunch of things together and trying to put it together into something that works well. It's actually pretty easy to do if you use a couple rules of thumb. And those 2 rules of thumb are, generally speaking, you want your string voltages, so all the strings that are in parallel, to be within 10% of each other in voltage. And then you want your modules in the string to be within 10% of each other in current. So as you see here, I've got 60 cell modules up here, 36.2 volts and 4.5 amps. String voltage is 144.8 at 4.5. Then I want to go back and add 3 72 cell modules because I found a good deal on them. And the amperage is 9.5 amps. So it's 142.5 on the string voltage and 9.5 amps on the string current. So when I put those 2 in parallel, you see the amps add together and I get about 15 amps, 14 amps, and the voltage is close enough that the MPPT tracking algorithm is going to find the correct MPPT voltage for those. So that's going to work just fine. That's going to be a nice little setup. There's not really going to be any loss to speak of there at all. And as I showed here, you're running your MPPT voltage is going to be right around 143, and we're going to be about 14 amps short circuit current. Now, here's a couple more examples of modules in series. And you see I got 36.2 volts all the way across, but I got 4.5 amps on this first one and 8.5 on those 3. This is not a good idea because now what happens is this is your weakest link in the string. So this string is going to put out about 4.5 amps. So you're going to lose half of these 3 modules by doing that. So, in a perfect world, you would not do this. You would take this module out, you would add another one of these, you'd just come up with another way to do it. But this is what I was saying about the voltage in series doesn't matter. The current in the series string matters. So this example down here, we look at these module voltages. Not sure where we would ever find these modules, but if you did, these would work just fine in a string. The current is all really close to each other, so you're going to get about 9.3 amps out of this string. And you're going to add the voltages together, and that's going to be your string voltage. So again, solar salad. Any questions, definitely email me, sales@midnightsolar.com. Happy to help you, mix and match panels. It's becoming less of an issue now with module prices being where they are, but back when they were $10, $12, $14 a watt, this is a really common thing to run into. And then we talk about max wattage. So here's another one that's this is a pretty common mistake I see, depending on how it's all worked into the system. So a lot of equipment out there in the battery-based world cannot be overdriven. And what I mean by that is, like, if you have a grid tie inverter, if you got a 5 kilowatt SMA grid tie inverter, you might stuff 7,500 watts of PV on that so that you run it pretty much hot all day long, against the limit. And knowing that modules only put out about 80% of their nameplate anyways, it's not going to be really that big of a deal, and you're maximizing your cell to the grid. Now, on a charge controller, a lot of charge controllers will have issues with that. They'll do things like nuisance trip the battery breaker, um, different things like that. So you have to be really careful with that. You have to really look at the manufacturer's specifications. An example of that would be like the Snyder XW MPPT 60. They recommend you use an 80 amp breaker on the output of it because it will overshoot the 60 amps on occasion and trip a 60 amp breaker if you put one on it. All the classic line, I believe all the Morningstar line, for example, they do very well at regulating their output current. So on a classic 150, if you have the current set for 80 amps, it's not going to exceed 80 amps. You can put 200 amps of PV on the thing if you want. It's going to regulate right at 80 amps very, very nicely. Now, with that said, there's also sometimes where it's a good idea to overdrive a charge controller, and sometimes it's not. If you're designing an ideal off-grid system, then overdriving the controller a little bit makes some sense, because on a perfectly sunny day, you're not going to use the whole array anyways because the batteries are going to get full so quick. But on a cloudy day, we're going to be able to maximize that harvest a lot more and get a little bit more out of the same amount of money out of that charge controller. As now the charge controllers are adding quite a bit of cost to the system, with PV being as inexpensive as it is. That said, if you're doing a battery-based grid tie system, I tend to recommend not exceeding like 80% of the current rating of your charge controllers, be it Midnights, Morningstars, Outbacks, anybody's. I think it's a good idea to limit that to about 80%, just because they will get hot as the day goes on because they're running wide open selling to the grid. Whereas in an off-grid system, as soon as the batteries start to get full, it regulates back and backs the current down. But in a grid tie system, everything's running wide open all day into the grid and selling that production. So just for longevity, I don't like to run my electronics at 100% all day long like that. That being said, all of our electronics, all of the other companies I mentioned, they're designed to do that. But I just personally don't like to design a system in that respect, and I definitely don't want it clipping all day. I don't want to put enough PV on a classic 150 that it's exceeding its current limit on the output side and having to throw away PV, because then I'm just losing kilowatts into the grid. So we're going to talk a little bit about rapid shutdown. There are a lot of slides in here, so I'm not going to bore everybody with reading everything verbatim. If anybody is running into rapid shutdown issues with off-grid systems or battery-based grid tie, and I don't cover enough here to help, definitely raise your hand or feel free to reach out to me after the webinar. But it is a challenge. So everything out there really is designed for 2017, especially NEC, is designed around grid tie inverters. And everybody tends to not really pay attention to the battery-based world because it's a small percentage of the overall sales. So that being said, what are some of the issues you're going to see? If you try to use product that's designed for grid tie inverters and isn't specifically tested with charge controllers, some of the issues we see are switching noise from the controllers. Charge controllers are notoriously more noisy than a grid tie inverter on the PV array. They have a lot more switching going on inside. They're going down to a very low voltage. And everybody's, not just Midnight's. Midnight probably has one of the cleaner ones, but they're all going to make some switching noise. And then we have the bleed down of the caps in the charge controllers. So there's a couple things there to be aware of. We have done a lot of extensive testing with the Tygo TS4F, as well as with the AP Smart rapid shutdown device. We do also have our own device that's headed off to ETL probably any day now that will do module level shutdown as well. And all three of those have been very extensively tested with charge controllers. Every brand we can get our hand on, and we're seeing no issues there whatsoever. So what we're going to talk about a little bit is how to conquer some of these issues on the Classic when you're doing rapid shutdown, and some of the common mistakes that you can make as you're doing that. So our current model of little SOB, as I mentioned, is not compatible with charge controllers. Look for us to have a model on the market probably in about a month and a half that will be. The new products are all SunSpec compliant, and that's not a huge deal, but what that means is that they all share the same communications protocol. So if you have a device, let's say one of our new charge controllers that's not out yet, or a grid tie inverter that says it's SunSpec compliant, it's going to transmit a specific signal that these devices then listen to and work with, and you can rest assured the two work together because they've been certified by SunSpec to do so. Tigo is not SunSpec certified. They do follow roughly the same protocol, and it does seem to work together. So your mileage may vary there. You may want to plan on using Tigo's transmitter, but the AP Smart, the Midnight stuff will all be SunSpec certified. So you would use one of these per solar module to meet 2017. Anybody that's not aware of 2017 NEC, that's a whole webinar in itself. But basically, they're requiring us to bring the PV array down to less than 80 volts between any two wires or any wire and ground within the array itself, and below 30 volts between the array and the charge controller. So they're essentially limiting us to one module worth of voltage anywhere in the array, and that's why we basically call it module level shutdown. You really have to have a device on every single solar module. Some of the things we can do is how do we power the transmitter? Some transmitters can be powered right off the auxiliary in the Classic. Some require like a DC to DC transmitter. One of the things I'll point out is that a lot of transmitters run on AC because, again, they were designed for the grid tie world. Using an AC transmitter on an off-grid system doesn't really make a lot of sense because if the inverter goes into low battery shutdown, your system is going to go into rapid shutdown and your charge controllers quit working, and now you have no way to charge your battery. So if you're doing a off-grid system with rapid shutdown, I would absolutely recommend getting a small DC to DC converter off an Amazon or something and wiring that up to your transmitter and using a 12-volt transmitter or an auxiliary off a charge controller if it'll power it. So that's something to be aware of. I've seen that one happen a couple times now. It didn't really get thought of until after the fact, and it's like, oh, how do we charge the batteries? The other one is to remember that battery breakers will not always initiate a rapid shutdown. So we're allowed to use different switches and devices as initiators. And on a Classic, for example, or an Outback charge controller, I can't speak for the other brands, I haven't tried it, but if you walk up to a running Classic in the middle of the day and you unhook the battery breaker, shut the battery breaker off or disconnect the battery from it, it continues to run. It goes into absorb or float and just sits there and continues to run, harvesting enough energy to power its internals and stays running. So if you had the transmitter powered from its auxiliary, and you went over and shut off the battery breaker, all you're doing is just disconnecting the battery. It's still going to keep the array alive. So in a case like that, you'd probably want to use like the PV array disconnect for the initiator, or even just a separate breaker that goes to the transmitter to break that 12 volts. So just be aware of that. That's one of those things that can kind of catch you by surprise. And all the same stuff for the AP Smart. As I said, it is SunSpec certified. So when you're looking for rapid shutdown products, you really want to look for this logo right here. This is going to make your life so much easier as you go down the road, knowing that everything works together. If you've got a Midnight Barcelona 600 volt charge controller and you see this logo on the side of it, you know it's going to talk to an AP Smart or a Midnight LSOB or whoever other's brand it is. So this is pretty key for you guys, because up until now this industry has been very much we'll all do our own thing and go in our own direction. And as an installer, when you're out there in the field, you're scratching your head like, I wonder if this is going to talk to that, and I wonder if this is actually going to work. And it's always just a lot of trial and error. With SunSpec involved now, that's pretty much a guarantee to you guys that if one person's inverter is SunSpec certified and one person's module level shutdown is SunSpec certified, you can rest assured those two are going to work together, and one manufacturer is not going to point at the other one, which is the other issue you're going to run into. If you throw something up there that hasn't been tested, like a Tigo, and then you put a Midnight product in there, Midnight may be a bad example because we try to support everything, but if you call up Tigo, they're probably going to tell you to call us. And if you call us, we're going to be, well, you should probably call Tigo. When you start seeing that SunSpec logo, now you know that we've all been tested to work together, and we're going to tell you, okay, yes, let's make sure we're putting out our signal. Yes, we're transmitting our signal. The wiring is correct. We need to get AP involved and figure out why they're not turning on, or vice versa. So it just, there's a line in the sand where the support stops for one manufacturer, starts for another, instead of being gray for you guys. We're not going to go through a lot of this. This is that stuff I told you that we could talk about for an hour. This is our local application software that allows you to monitor, log, and program all of our charge controllers. Our classic charge controllers. And this is, basically what I was running you through here would be how to set up auxiliary 1 to power a transmitter, for example. But we're not going to spend a lot of time on that because there's a lot of slides left here to go through, and I don't want you guys to be stuck here for 3 hours listening to me. but as you can see, it's pretty easy to walk through. So then we talked about bleed down. Those that don't understand what I mean by that is NEC, National Electrical Code, requires us to have the wires between the electronics and the array drop to less than 30 volts in less than 30 seconds. So just unhooking the PV array is not always enough. An example of that is on a classic or an Outback charge controller. They will keep their relay closed and hold the input voltage where it last was for about 90 seconds. Because they basically don't want to keep switching back and forth on you. They want to minimize that relay clicking and not irritate you. Nothing other than that, but that's just why they do it. Some grid tie inverters do that, and others. So what we need to do is we need to tell the classic, for example, that, hey, when your PV wattage drops below X, we need you to wait only 5 seconds, and then we need to open your relay. So what we're doing here is basically walking you through how to change that value from 90 seconds down to 5 seconds. And then what happens is once you initiate a rapid shutdown, the PV voltage drops, the charge controller waits 5 seconds, opens its relay, and goes into resting, and the input capacitors drop almost instantly because the SunSpec compliant module level shutdown actually presents a load to the capacitors when they're in the off state to do just that. So that's a very elegant system, and it's a very simple setting in the classic. And there's just a little bit more on how to set it. Before we go into this one, I do want to say with rapid shutdown, the one thing I encourage you to do is system checks and function checks. Don't wait until the inspector gets there to push the button for the first time or flip the switch. Just don't get caught off guard like that, because it puts you in a position where you're uncomfortable, you're on edge, you're a little anxious because now something is not doing what you expected it to do. So definitely always do your function checks. It's just like when you do an AC coupled battery based system, always run it through. It's overcharging of the battery to make sure it shuts down, and all those different items. Don't ever walk away from something like that. So voltage. We've talked about voltage a few times, but it's one of those things that can get you in trouble in places if you don't pay attention. And sometimes it's not necessarily cut and dry and clear for you guys what we're talking about as a manufacturer either. This particular box right here is rated for 600 volts DC. The fuse holders are rated for 1000 volts DC. It just happens to be what the manufacturer sells. But if you look at the box, you look at the label, and you look at the marketing material, it's going to clearly tell you the limit is 600 volts. And this is what happens when you put 1000 volts through it and the switch opens. DC does not like to open under load. And when it does open under load and the switch is not designed for that voltage, it will catch on fire. It will melt down. So this is what happens when you exceed the voltage of a device. So make sure your DC gear is rated for what you're doing. There's some thought process to this too that I like to bring up, in that we don't always look at the system from the right end, if you will, maybe. An example of that would be, let me just say, I'll pick on myself and say, okay, I have a classic 250 in my truck, and I'm running out to my customer's house, and I'm putting 24 volt system in. I've got two 60 cell modules I get in series. So I've got, I've got maybe 80 volts max VOC. Going into a classic 250 because that's what I had in the truck and I didn't want to wait for a 150. I throw that all together. I'm like, hey, I'm at 80 volts. I'm using a regular combiner. I'm using 150 volt breakers. I'm going to put an SPD 115 on there. Life is really good, right? The system is actually designed, and it's okay. Everything's rated for 80 volts. The problem comes in is that when somebody else comes in behind me, or I come back in later and forget about it, and I realize that, hey, I got a 250 volt controller there. I could just add two more modules in series instead of adding more strings, and now I've exceeded the voltage of something. So my general rule of thumb and my recommendation to you guys is that when you're designing a system, make sure the voltage rating of everything in the system matches the maximum voltage of the power electronics you're using. Don't base it on the array, base it on the power electronics. So in that same example, I would recommend using a 250 volt breakers and at least a 250 volt SPD, or the SPD 300 in our case, which we'll talk about later. But that is another mistake I've seen in a couple of cases where somebody will go in and design a perfectly working system, but then somebody will come in behind them and expand the strings instead of putting more strings. They expand modules per string, and that does get you in trouble. Load break rated. That's huge. Definitely look for that in DC. Those of you that don't really know why we talk about this, we do have a video up on our website about the demystifying DC breakers, but the issue here is, and you can't see my hands, I talk very well with my hands, unfortunately. On an AC signal, on AC voltage, if you will, going through a breaker, you've seen that sine wave, and it goes up and down and up and down, and it crosses that central line 120 times a second. And every time it crosses that line, there's 0 volts and 0 current. So at 120 times a second, there is no potential for arc inside that breaker. And that breaker gets to open basically unloaded, if you will. I mean, I know it's still got a load on it, but it's got that time to put that arc out while it opens. Now, if you look at DC on like an oscilloscope, there's no wave. It's just a straight flat line. It is always on. So that breaker has to deal with that arc the whole time it's opening. It's very important that it's load break rated, it's DC rated, and it's rated for the voltage you're going to run it at. The other question I get a lot is, hey, I got a charge controller that the VOC is 200 volts, but the MPPT is 150. Can I use a 150 volt breaker? And my answer will always be no on that again, just because it could be a dead short. It could open at 200 volts, so just don't trust that. Combiner boxes, next step in the system. Seemingly pretty simple and pretty straightforward. Do know that we have your back. You can always reach out to Sue. She'll tell you exactly what you need for combiner box. But we have things from 150 volts all the way to 1,000 volts. We have disconnecting combiners. We have non-disconnecting combiners. We have models that use fuses, models that use breakers. We have some models that are rapid shutdown compliant for 2014 NEC. So we have quite a few different things, pass-through boxes, battery combiners, just a lot of different varieties on our website. I won't bore you with all that, but do know that you do need combiners. We will talk a little bit more about that later, but just remember that with strings of modules, a string of modules has what's called a short circuit current rating, or a series fuse rating, I guess is the best way to say that. Typically going to be 15 or 20 amps, right? So if you was to put 2 strings of modules in parallel, and one shorted out internally, the other one doesn't produce enough current to exceed that series fuse rating of that string. But if you was to put 3 or 4 in parallel and one shorted out, those other 3 can generate enough current backwards into that shorted out one to actually catch something on fire. And that's why we fuse each string. So then that 15 amp breaker would blow because it's being backfed 45 amps, and it would trip and open up that string and eliminate the fire. So that's just something to keep in mind. There is a very good reason for fusing every string. It's not just so Midnight Solar can make money, trust me. And I kind of just told you why we need a combiner. And that said, you can also understand why this wouldn't be considered a combiner, correct? This is, with what I just told you, this could potentially feed, 5 strings into one string when it shorts out. So something to keep in mind. And the same issue applies to batteries. This is another one that I see get missed sometimes. I'll see 7 or 8 strings of batteries, which I don't recommend anyways, but I'll see that, and there's no series fusing on each string. And the same thing can happen. If a single string of batteries, if that battery should short out internally and another string is sitting beside it, the current coming back to it probably isn't enough to cause big problems. It'll probably drain the good string, and things will level out. But if you have like 4 or 5 strings of batteries and something happens internally to one battery and one string, then those other 4 or 5 can backfeed it enough current to cause a problem that's going to be much more catastrophic. So series fusing on your batteries is, in my mind, just as important as on the PV array. And it makes it much easier to troubleshoot and maintain those batteries if they're of a lead chemistry as well. You can take one out of the string by opening the breaker and clean connections, do whatever you got to do without shutting the whole system down if you need to. So common issues with combiner boxes. Follow the manufacturer's directions. This troubleshooting call came in was a ground fault issue, and Those of you that are familiar with our breaker boxes, these little bus bars are supposed to go in the top of the breakers, and you tighten the set screws down on them. This person had somehow got it in the DIN rail, and has still managed to get the breakers on the DIN rail. So the PV positive going to the Classic is actually shorted the ground right there. And that was causing a ground fault on the Classic. And when we finally got pictures and found this, then it was easy enough to figure out how to fix this, and we got them right on the right track. That being said, this prompted me to look at our manual and realize, we don't spend a whole lot of time explaining to you exactly how to install all this, like, picture by picture, step by step. I think there's some assumption made by all of us manufacturers, not just Midnight Solar, that every one of you has some level of knowledge of our products. And when you see a breaker with the set screw on the top and the bottom, you probably assume that you put something in that set screw. So don't be afraid to call and ask questions is what I mean here. If this isn't clear to you and you're opening up our manual, definitely reach out to us and say, hey, this isn't quite clear to me. Can you tell me what to do here? And chances are we'll probably also have Todd edit the manual at the same time and clarify the manual. Because if somebody is confused by that manual, then we can rest assured that somebody else will be in the future. So we try to be very proactive about that. Here's another combiner box issue. This mistake started at Midnight Solar. We sold this combiner box as one of our AC micro combiners, and those are made to combine 3 strings of microinverters at AC, 120, 240 AC. Production put the wrong bus bar inside the box, and the installer didn't really catch on to the fact that he was hooking L2 and L1 from his 60 amp breaker in his load center to the same copper bus bar. So as you can see, you've got 1, 2, 3 strings of N-phase micros here, and they go into a single solid copper bus bar. So every time he'd turn his 60 amp breaker on in his utility panel, it would instantly trip. And he called for assistance on troubleshooting this. And I said, well, how about a picture of the breaker box, combiner box? And as soon as I said it, I'm like, oh, that's the wrong bus bar. And you sent me the label. And it's like, oh, yeah, we made a mistake in manufacturing. So I guess the reason I show this is mostly to just show you that it's not always the manufacturer, it's not always the installer. If something doesn't seem right, it could be us, it could be you. But again, don't be afraid to call, and we'll get through it. We'll solve the problem. Here's another good example of a tech support call. Complaint was the controllers wouldn't wake up and make any power. Looking at the Classics, they had about 30-something volts on each one, which is typical of them on a 48-volt battery because they have a charge resistor internally that keeps a little bit of voltage on the input capacitors so that they don't get slammed when the relay closes. Looking at this breaker, I'm like, oh, okay, these are 300-volt breakers, and if anybody's ever played with our 300-volt breakers, they have this factory-installed copper bus bar down here at the bottom, and that is to put 2 poles in series, because remember, each pole is 150 volts, so if 2 in series, we're 300 volts. So the way these are supposed to be wired is we would come in the top, I think you can all see my mouse, we would come in the top with the PV array into the positive emblem, and the bus bar would go into the negative array and then go out to the charge controller. So the power voltage would come in through this pole, through that copper jumper, and back out the top. But in this case, they removed the jumper, installed the bus bar and the plus up here, and the PV array and the plus down here. So there's no physical connection between the 2 poles. So there was never any voltage at the charge controller. Again, looking at the manual, we do show it wired up here, but we didn't actually tell you, do not remove the factory jumper on the breaker. We, again, assumed that was a given, and, well, you know what assuming does, right? So we work diligently to try to make our documentation better every day, and anybody that's got any suggestions, definitely reach out to us. So now we've gone from the PV array down through the wiring into the combiner box, and now we have to pick a charge controller, and we have to understand what we're doing with our charge controller. So as we talked about before, the current charge controls are based on current, and that can be confusing. We take a few calls a week where the customer wants to know, how many watts can I put on my charge controller? We'll ask them, well, what battery voltage are you going to be running? Well, we're not sure yet. Okay, then it depends, because unlike a grid tie inverter or a battery-based inverter, charge controllers are done in amperage. So when we say a controller is 10 amps, for example, that means that at a 12-volt battery bank, it's going to be able to process 120 watts. 240-volt battery, 24-volt battery bank is 240 watts. 48 volt battery bank would be 480 watts, just as an example. So you can see where the amperage, it's part of Ohm's law, and that's what causes the change in wattage based on the battery bank voltage. Uh, we typically like to recommend a 48 volt battery if it's going to be off grid, um, like residential or even a medium sized cabin. If it starts to get into a small system, 12 volts or 24 volts can make a lot of sense. But the currents just go up so fast on 12 volts that you really don't want to be using more than like a 1,000 watt inverter on those systems. If you're really going to go that big of an inverter, you really just move up to 24 volts or even 48. So we start out with the BRAT, which is a PWM controller. It's a 20 amp controller with a 10 amp load circuit. And if you do not need the load circuit, you can parallel those two internally by flipping a jumper over here and wire them together. And you can make this a 30 amp charge controller. It's selectable for 12 or 24 volt battery by one of these dip switches right here. And it will charge a flooded, a gel, or an AGM. We do get a few calls on can I use the BRAT on a lithium battery, and the answer is yes and no. It is accurate enough to charge a lithium if the lithium has the charging algorithm matches one of its presets. So unlike all the other controllers we're going to show you here in a minute, the BRAT has 3 or 4 or 5 preset charging algorithms that you can select by these dip switches up in here. So if you were using a lithium battery and one of those algorithms would match the voltage requirements of the lithium, then you could use the BRAT. One word of caution, you do need this little blue wire right here is a thermistor that monitors the ambient temperature and adjusts the battery charging voltage based on that. So you would want to clip those two wires and disable the battery temperature sensing and compensation if you're charging a lithium. And the same is true for any charge controller. If you're charging a lithium battery, you really don't want the temperature sensor in the system because the lithium doesn't really care about the temperature when it comes to charging to the proper voltage. Whereas like an AGM or a lead acid battery needs to have its voltage set points changed based on the temperature. So a typical flooded lead acid battery, we'll pick on Trojan for example, may want you to charge to 59.2 volts. That 59.2 volts is at 77 degrees Fahrenheit. As that battery goes colder or warmer, that number has to change. We all talk in Celsius because that's what most of the world's used. So 25 degrees Celsius is the neutral point where no compensation happens on a battery. If that battery is, say, 15 degrees Celsius, then we're 10 degrees colder than what the battery wants, and we have to raise the battery's voltage to properly charge it. Most manufacturers use 5 millivolts per degree Celsius per cell. Now, that is adjustable on our Classic and Kid, but that is very common for just about every lead acid battery I've run into. What that means basically is on a 48 volt battery bank, if the battery is down around 10 or 15 degrees C, you may see 1.5 volts extra at your absorbed voltage. That 59.2 may all of a sudden become 60 volts. And that is a very common question that we get every fall. People will call and say, my controller is overcharging my batteries. And it's like, no, it's not really overcharging it. It's charging it to the proper voltage because your battery is cold. And we get the same, but in the reverse order in the summer. Your charge controller is not properly charging my battery. It's stopping before it gets to the set point, and that's because the battery is too warm. So just things to keep in mind, little tidbits of information that you will run into and see. The BRAT is outdoor rated. It is the only controller we make that's outdoor rated. You can physically nail that thing to a tree. Sue actually has one nailed to a telephone pole with a solar module on it that's powering a light on her mailbox. So pretty cool little device, gate openers, small systems, a lot of good uses for these things. We talked quite a bit about this, but it's all adjustable internally. It does have 4 LEDs up at the top that will tell you what's going on. Is the load on? Are we in low voltage disconnect, etc.? It has a 16 position rotary switch over here to select from a whole different variety of things to do with the load. Comes on for a couple hours at night, a couple hours in the morning, or just a couple hours at night, no hours in the morning, or it's on dusk to dawn or dawn to dusk, or just on all the time until it's low battery. There's just a lot of settings there you can use. And then you have your dip switches over here for setting the different battery chemistries or voltages, whether it's in parallel mode and not using the load circuit, auto EQ, stuff like that. And that's just a better example of that. So, and anybody that wants this slide deck can email us. We will send it out as a PDF. It'll also be up on our YouTube channel probably in a couple days and be available for viewing there as well. So back to the fun stories. Again, like I said, if you send me a picture and I think it's worthy, it's going to end up in one of my slide decks. This one came in, I'm not sure how well you're seeing it on your computer screen, but up at the top of the pole is a solar module. And there's a sign down here that's supposed to light up. And the complaint came in that we had a couple faulty charge controllers, and they weren't turning the loads on when they were supposed to. And after troubleshooting, our technician determined over the phone that the batteries were dead. So he asked for some pictures, and this is what he got. And, solar modules need to be in the sun, right? It's just an example of a multi-layered contracting system on a job site where once it got down to the guy installing it, he was not aware what that thing even was on this piece of equipment. He was a contractor that was designated to drill holes and bolt stuff in where the plans called for, and unfortunately it didn't work. The customer was really upset with us, thinking our product was faulty, but then, once pointed out, they made rectifications. But those are the things that you run into, and that could have taken a couple hours of troubleshooting if we hadn't asked for a picture. So then we'll move into our next charge controller up, which is what we call the KID. It is 30 amps. It is MPPT. So typically speaking, anytime we're doing a system of more than one or two modules, we're going to be looking for MPPT. We really want to maximize our investment. And MPPT allows us to design the array at a higher voltage than the battery bank, smaller wires, more efficient, et cetera, et cetera. So the KID is great for cabins, boats, RVs, similar applications to that. We recommend it's around 500 watts on 12 volts, 1000 on 24, 1500 on 48. It does have a very sophisticated lighting controller. It does have auto gen start, 2-wire auto gen start, where it will actually monitor the battery voltage and tell you if the generator started or not. It also says available for wind or hydro, which is not true. I need to remove that off the slide deck. Few highlights of the KID. One of the things I really like about it, these LEDs over here on the left-hand side. These top three will tell you when the last time the battery went to float. If the green light's on, it's been in float sometime within the last week. If the orange light's on, we haven't been to float in 7 days. If the red light's on, we haven't been to float in 14 days. So those are just quick at a glance. The customer calls, says, my system's not holding the voltage through the night. Which light's on the top? Is it red, orange, or red? Green, orange, or red. Quick at a glance what's going on. And the rest are pretty explanatory. Float light is on anytime the controller's in float. OVR, this one we do get a lot of calls on. OVR is kind of misleading. People think it's over something, right? And it is. It's over the current limit. This is just telling us that the KID is processing 30 amps and it's having to limit its input because it's at its maximum of 30 amps. So when you do kind of push the boundaries on the amount of wattage you put on this KID, on a good sunny day at noon, that orange light comes on. That's perfectly fine. That's normal. Error light for different errors of the AGS didn't start. And then the CLP, the bottom blue light is on anytime the load circuit is active. And here's just a quick example of a flow diagram. You'll notice this fuses in the face of the KID. That was because we realized that a lot of people don't use fuses or breakers. And it's pretty scary. And I can't tell you how many times I've been on the phone with a customer and I said, okay, we need to reboot the charge controller. And what do you mean reboot it? So we need to remove the power from it till the screen goes dead and then, reapply the power. And they'll say, okay, wait a minute, let me get my wrench. And what do you mean your wrench? Well, I have to unhook the battery cable. And then the inverter goes dead because they unhooked the battery cable and their cordless phone shuts off and you're not sure if they died or if they just lost their power. So definitely breakers. Always need breakers, disconnects. Don't wire up an inverter or a charge controller without these. First of all, it's dangerous. There's a chance you could burn your house down. And second of all, it just makes it so hard to troubleshoot and to, diagnose things. I know breakers seem expensive sometimes when you're kind of a do-it-yourselfer and you're piecing things together. You're like, oh, you want me to buy a $15 breaker, really? But in the long run, it's going to help a lot. And if there ever is an issue, your wood stove catches on fire and you end up with a fire marshal at your house and he sees the solar system and he walks over and doesn't find any breakers anywhere, they like to point fingers It's just cover your own butt. It makes the system safer and much easier when you call us for support. Then we move into our biggest charge controller at the moment. This controller comes in a 150, a 200, or 250 volt operating window. It supports up to a 72 volt nominal battery voltage. The regular classic has ground fault and arc fault protection built in and included. All regular classics do solar, wind, or hydro. And they also have manual and auto EQ. And they're fully internet capable. So you can hook the classic up to the internet. You can use a function we call My Midnight, which I think we show later, or the local app, and allows you to program and monitor remotely. The display on the classic is able to be remoted off the classic. There's just 4 little screws in there to hold it in. Or you can add a second display. There's a couple ports on the classic. You can plug a second display in. You've got one out in your power shed and you want to display in the house, you can do that. They both will allow programming of the classic at that point. So that's kind of nice. The classic stores 380 days of history. Basically what it'll do is it'll take a snapshot every day, like kilowatt hours for the day, high battery voltage, time and flow, things like that. And it stores 380 days of that. It also stores 24 hours of snapshot data at 5-minute intervals. So every 5 minutes, it just takes a snapshot of wattage, battery voltage, input voltage, etc. And that's kind of nice, because if you're really trying to diagnose something really down into the weeds, sometimes being able to go back and look through the day like that really makes it a little easier to do. It does have a openly published Modbus protocol that it speaks, and it can speak that over Ethernet or RS-232. You can parallel a lot of them in a system using what we call Follow Me. So they would all have their own single PV array, and then they could all charge a single battery bank, coordinating to that battery bank. So each classic would have its own PV array, but they all tie to a single battery. Then we have what we call the SL version. So you'll see like the Classic 150 SL. And it's SL actually stands for sorta light, because some of you may remember we had the Classic Light that had the not a display, that had dip switches and LEDs. And that just turned out to be such a troubleshooting issue for most people that we did away with it and we made what we call the SL. The SL basically removed the internet, it removed the arc fault protection, and it removed the wind and hydro modes to simplify the menu structure. So let's just say it's a more simplified product that still does everything the regular classic does except for arc fault and internet and wind or hydro. So now I'm going to tell a little story. This is one of my favorites. This call came into one of my tech support employees, one of my lower level support guys, and the complaint was that he had 6 strings of modules in parallel, and the classic is not using the 6th string. And, you know, my tech had walked him through shutting off breaker 1, 2, 3, 4, and 5, and obviously saw a drop in current every time they did one of those. Every time they shut off breaker number 6, they saw no change at all. And the customer was getting impatient. My tech was sort of at the end of what he knew to do. So it got forwarded on to me. So I started asking for some pictures. And I said, you know, we have to start at the PV array and we have to work our way through this, because the classic physically can't ignore a string, obviously, right? I mean, they're all parallel on a single wire. So if you remember before, we showed that combiner box that we said we'd talk about later. That was the combiner box, and the customer removed the locks on the MC4s so they could plug and unplug them quickly to troubleshoot. So this was the combiners. Now, okay, I mean, while that's not okay, and I did explain why that's not okay, electrically, it's not causing the problem we're seeing. So we don't focus on this, and we move on to the next problem. We figure out what's going on. So I said, well, send me a picture of the array. I need to see the array. And I get this. So I'm like, okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You said 6 modules. He goes, yeah, there's 6. He goes, look closely on the right there. I'm like, oh, now I understand why it's not making any power off the 6 module. It's behind the bushes. So the moral of that story is this phone call took probably a little over an hour and a half of Midnight's time to get to this point. And these things happen. We all do things. I mean, I've melted terminals off batteries before, so any of us that have never made a mistake probably aren't installing this stuff. So my moral of the story is, yes, they need sun, and always ask for pictures. So when one of us asks you for a picture, there's a reason for it, and it's not just so we can put you in a slide deck later. It's usually because it just helps us see what you're seeing. It makes it so much quicker to get to that end goal, which is to get you back running. This is at my midnight online portal we're talking about. It's a great troubleshooting tool for you guys, especially you installers out there. Customer calls and says, hey, my batteries just don't hold overnight anymore. You can sit there with the coffee in your hand, you can pull up your computer and you can look at this and say, okay, well, I've looked back through here and I've noticed you haven't gone to float in the last 45 days. What did you do back here? Like, oh, well, that's when we bought the new hot tub, or whatever the case may be. Just a quick at a glance, it really does let you see the system as a general overview and get a little better idea what's going on. So I'm not going to spend a lot of time on new products because I know we're going long on time, but just know that we've got a couple new charge controllers and some new inverters coming out to fill your needs. The new charge controllers will be 600 volt. One of them will be dual input, the other one is a single input. They're 80 amps per input, and so on. So again, we won't go too deep down that rabbit hole because it's just well, I've already kept you for an hour, and that's what it looks like installed. The new inverter, 5,000 watts at 48 volts. There'll be a 12 volt for 2800 watt model as well. We're probably still, I'm going to guess, about 8 to 10 months away on this one for public consumption. Hopefully a couple months on beta testing. And then the B17 system, which probably everybody has seen by now because we've been talking about it for 5 years. This one is looking like it's about probably 6 weeks away from beta testing. And then we're going to get back into actually the wiring of the inverter, the charge controllers, the batteries. This example here, this was grid tie installer's first battery-based system. The complaint was there was liquid running out of the bottom of the inverter, if I remember correctly. My coworker Tom handled this call. And we started looking at it, and he's telling us there's 8 strings of batteries in parallel, which is not a great idea to start with, because they don't share equally. But then we started looking at the pictures, and we're like, 1, 2, 3, 4, 5, 6, 7. Oh, there's an 8th string up over the inverters. And all of the power was going up to this string on top and then going down across through these strings. So now when all 5 classics would hit, or 4 classics would hit at full charge current, that's a lot of current going into this string of batteries. And then the resistance in the wires, it's less and less current for every string of batteries as it goes down. And it was actually boiling these ones up here and actually pushing the acid out of a sealed battery. So if for some reason you have to do multiple strings of batteries, then you really want to use something like a battery combiner box, and you want to use equal length cables for everything. So you want all positive and negative cables from the strings to the combiner box to be the exact same length, and you really don't want to route metal conduit through your live battery box. Also, your inspector's probably going to frown on your plumbing tees coming in from your PV array. So there's a few little things here, right? It's like, okay, well, he didn't buy the GSLCs from Outback, the load centers. He saved some money and bought the mini DCs from us. And technically it'll work, but it made his install a lot harder. It spread it out a lot more, and it didn't give him any place to put everything. So a lot of those little things, like if you're a grid tie installer and you've never done a battery-based system before, give us a call before you actually bite that off. It's not really a real complicated thing to do, but there's a lot of things that will surprise you if you're not familiar with doing it. And we have a lot of experience on staff. I mean, myself as a licensed master electrician, been installing this stuff forever. Jim Parrish, who's a certified NABCEP instructor, been installing this stuff forever. Todd lives off grid. We just have a lot of manpower here that eats and breathes this, so that that's what we're here for, is to help you with that. So we talk about end amps. Now we're charging the battery. So we've gone through, we've talked about some of the mistakes on the battery. You're doing a lead acid battery. in an off-grid scenario, you're probably going to overcharge it on a regular basis if you don't use end amps. Because essentially what happens is, if you look at a 3-stage charge algorithm, we charge uphill in bulk until we hit the set point, which is like 59.2 for a Trojan battery. And then we maintain that for a period of time, 3 hours, 4 hours, whatever the manufacturer recommends. There's some generic formulas for calculating that, but I really, always strive to go to the battery manufacturer themselves and get that information. And then we drop into float after that period of time. So now if you've got an off-grid system and we get 7 days of sun in a row, that battery is nowhere near as depleted in the morning, and that absorb time doesn't need to be as long. So if you keep hitting it with that 4 hours of absorb every day, you're prematurely wearing out your plates. So what you can do is you can use a function called end amps that monitors the current into the battery with the Whiz-Bang Junior or shunt, and it will take the controller out of absorb early based on that end amps current, and only give it the current it needs to be, the time it needs to be fully charged. So now when you get that 3 or 4 cloudy days in a row and the sun comes out, you'll get that 4-hour absorb time. But when you have 7 sunny days in a row, you may only get an hour each day because that's all the battery needs. So that's something to be aware of. Always look at end amps. Always talk to your battery manufacturer, be it a Rolls or Trojan, whatever it is. That's a very important function to use properly. One of the things that we see a lot, unfortunately, is that people will take our equipment out of the box, hang it on the wall, turn it on, it starts charging the battery, and they assume it's done. And every single battery manufacturer out there has a little bit different charging requirements. And therefore, all of us manufacturers set our settings to the very lowest of anything we know of out there. So that if you've got a AGM battery, for example, and you throw our controller on the wall and turn it on, you're not going to over voltage that AGM and boil it. But if you do the same thing to a Rolls Threat flooded battery, you're going to undercharge the battery and kill it in a very short period of time. So always, always, always get those specifications from the manufacturers and properly program your power electronics to charge those batteries, especially now that batteries are becoming the most expensive portion of the system. So here we're just showing you how to set that end amps. If you're using the local app, it's a function here. You set it as a number, set it, tick it to use the Whiz-Bang Junior, save that. Something I will mention is if your charge controller doesn't monitor current into the battery, end amps is useless. So if you're using a controller, be it a Classic, a Morningstar, whoever's, and you don't have some form of current sense on the battery instead of just on the controller, it's not going to tell you anything. Because if your Classic, for example, is putting out 10 amps into the DC bus, and your inverter is drawing 12 amps from the bus, we're actually drawing 2 amps out of the battery, not putting any amps in. So the controller really doesn't know what's going on with the battery. It just knows what the bus is seeing, and that's why it needs that external current shunt, like I talked about with the Whiz-Bang Junior. So definitely, make sure your system is capable of monitoring the battery using something like the Whiz-Bang Junior on the Classic, or like an FNDC on an Outback, for example. So surge protection, utterly important. It will help. It will help if there's a nearby lightning strike. I have seen it actually help in a direct strike, but I'm not guaranteeing anything in a direct strike. But do know that we have them for AC and DC. We have 115, 300, and 600 volt models. They are not just for renewable energy. Every main panel should have a surge arrestor on it, be it on any grid-connected home, whether it is solar or not. A lot of the problems will come in from the utility grid. Ours do have blue LEDs that come on to let you know that they are active. If the LEDs go out, that means they are no longer working, or they're on AC2 with a generator input, and they will only come on when the generator is running. They are 4X rated, so they can be outdoors. I do like to put them on every input and output of an inverter. So if I've got a Radian or an XW, I've got 2 inputs. I like to put 3 ACs on there to protect the inverter. Those inverters are expensive. I also put one at the utility panel, as close to the main breaker as I can. And then if I've got an outbuilding that's 50 feet out or longer, basically any wire longer than 50 feet, if there's something on the other end of that wire that's worth protecting, I put one there. The other question we get asked a lot is, what about surge protection for batteries? Well, we used to say don't put any surge protection on your batteries at all, not needed. But today we're seeing a lot of lithium batteries, and lithium batteries have these things called battery management systems, BMSs. And they're pretty delicate in a way. I shouldn't say delicate. That's probably an unfair term. They're subject to damage from surges in equipment. So now all of a sudden, what was basically a great big old lead acid battery that's a huge capacitor and could take thousands of amps for a short period of time. Now when that BMS sees that, the voltage spikes and all the electronics fry in the BMS. So if you're using a lithium battery, we highly recommend a surge protector on the battery as well to protect that BMS. And as we mentioned earlier, size that surge protection device for the equipment is connected to, not the actual PV array. So if you have that 80 volt VOC we talked about, don't use an SPD 115, use an SPD 300, so that if somebody comes behind you and ups the PV array voltage, they don't fry their surge arrestor. So E-panels, won't spend a lot of time on these. Just know that this is now, we're getting into the inverter. We're wiring up the inverter. This is where you'd connect your battery-based inverter, be it a Midnight E-panel, an Outback GSLC for a Radian, or Snyder's breaker box, whoever's it is. Always good to use one of these with your battery-based inverter. We look back to that picture with those two Radians and all those mini DCs. If they'd used a GSLC, everything would have been inside there, all nice and neat. The classics would have been right up beside it, and everything would have just fit really well. I know sometimes it seems scary to look at one of these and say, oh, you want me to pay $400 or $500 for a box? Well, when you start to think about what it does for you and what it gives you, it makes a very clean, legal install. And it gives you all of the connection points, all the proper overcurrent protection, the shunt to watch the whiz-bang junior, and, et cetera, et cetera. So it is really a nice way to do that. So transfer switches, or grid last, whatever you may want to call it. How do you use this power? Let's say that you have a grid connected home. You're putting in a small PV array and a Magnum inverter, for example, and your goal is really just to be able to use this power during emergencies. Whatever the case may be. You live in New England, you get a lot of ice storms. You want to benefit from that, but you don't really want to go all the way to a grid tie system and selling to the grid. There's ways to do that. Most of the inverters have functions that we'll call like grid last or opportunity, or there's some name to it. But most every battery-based inverter you're going to find out there from any of the big players like SMA or Magnum or Outback or Snyder are going to have these functions where they will prioritize the solar over the grid and connect to the grid as a last resort to power the loads to maximize your payback on this system. This picture here is just an example. This customer wanted to do his own. Each one of these plugs represents a load, and each outlet, the top of the outlet is like the utility, and the bottom of the outlet is from his inverter. So that for example, that top left one that says FR1, I believe, was the fridge. And when he wants to move the fridge over to the inverter, he goes and unplugs it and plugs it into the bottom outlet. Probably more elegant ways to do that, but hey, it works, and that's the main goal. But just know that most of the inverters can do that for you, and you don't really have to do something like this. That tends to be forgotten a lot, is that these inverters have a lot of functionality now that we may not know about. This is just a quick example of the inside of one of our E-panels, but just showing you, here's all your overcurrent, your bus bars connected to the inverter, all the battery breakers for the charge controllers, all the bus bars. Just a nice clean way to install. So I've still got a few war stories here. This one came to me while I was at Magnum, and the problem was the inverter kept going into low voltage shutdown. And I got this picture, and I'm like, that's the battery cable whittled down and stuck into the little bus bar that's made for the charge controller. Well, I look at that, and I'm like, okay, we do sort of tend to maybe mislead you because we say battery positive. But if you look down here, DC positive to battery, it's meant to go on this stud right here. So again, look at the manual. Don't always trust your first instinct on everything you see here, because this is misleading a little bit. But those battery cables being down there trying to push all 250 amps or 175 amps through this little bus bar. Similar situation, but different. 6,800 watt inverter running on number 4 THHN down to the battery bank. Yeah, just again, use the right size equipment, great size wire. It's a dual install, 2 XW inverters, and this is a 1.5-inch knockout. No bushings or anything on it, and all the wiring pushed back and forth through that knockout. So again, make sure you use the right strain release or the right bushings just so that things don't chafe and wear through. And probably one of my favorite ones, bus bars, C-clamps. There's a lot of story there. I won't bore you with the whole story, but again, pictures are worth 1,000 words. And my last and parting slide is, why do we care so much about verifying voltage? As an electrician, when I shut a switch off and I go over to that socket or I go over to that motor or I go over to whatever that may be, the first thing I do is check for voltage before I touch it. And this is why. There's no fault of anybody here. This blade on phase 1 broke off of the arm and stayed engaged. So if this electrician had gone over to that motor, that 3-phase motor, and decided to trust that and just start working on it, he'd have had 277 volts present. So always verify your voltage. So that kind of brings me to the bottom. I know I ran quite long. I don't know if we've got any questions, but if you do, feel free to throw them in the chat there, and Sue or I can answer those for you.
So far, it looks like no questions. We will go ahead and wait just a minute more in case somebody is still typing, just to make sure. If you do come up with any questions after the presentation that you're dying to get the answer to, please just send us a message over at sales@midnightsolar.com, and either Ryan or myself will be more than happy to answer any of those for you. Thanks for joining us today, and we appreciate you all being here. Again, if any of you do need the NABCEP credit certification, please send an email over to sales and we will get that out for you. We will also make the video of this available on our Facebook page, and we look forward to seeing you guys at a future presentation.
All right, I'll second what Sue said there. I appreciate everybody taking their time to listen to me ramble. As always, feel free to reach out to us if any questions, any concerns, and hope everybody's staying safe and not going completely crazy with the quarantines. Stay safe, and we'll see you in the next webinar. Thank you.